Okay, so first of all, let me thank Professor Fabio Miani for arranging all this. It's a lot of work for him to do, and I'm very pleased that he's managed to get so many people to participate. So I'm going to give 11 lectures, all on the microstructure and transformations in steels, and cover every major allotropic transformation that we get in steels. And you can ask questions through the chat line, which we can deal with towards the end of this lecture. So my first lecture, I'm going to focus on martensite, because martensite is one of the simplest of transformations that we get in steels, in the sense that we understand perfectly its mechanism, the atomic mechanism by which it forms. And here I illustrate the mechanism. So imagine that this is my parent phase, austenite, and it contains two different kinds of atoms. And this is a unit cell describing crystal structure of austenite. Then if you change the environment, for example, the temperature, the strain rate, etc., then it will want to transform into a body-centered cubic or body-centered tetragonal lattice. And if this is happening at a low temperature or a very high strain rate, in other words, a slow atomic mobility, then it will transform by a mechanism which is actually a physical deformation of the lattice. So we've changed from this kind of a pattern into this oblique cell. So this transformation should be regarded as not just a crystal structure change, but also a physical deformation, because look here, the external shape of the parent phase has changed into a different shape in the transformed region. And this is very important. You'll see that it has major consequences on the shape, etc., of the transformation product. So this is called a displacive transformation, because the atoms have moved in a very systematic manner to achieve the change in crystal structure. And you will notice that the neighbors of these red atoms have not changed at all, okay? Because there is no diffusion in going from here to here. So there is actually no composition change at all compared with the parent lattice. This is the interface between the martensite and the austenite. So what do we mean by low atomic mobility? Well, if we look at this equation here, this is the speed at which the interface between the martensite and austenite moves. This is the diffusion coefficient in austenite, and this is an interatomic spacing parallel, normal to the interface. So the units of a diffusion coefficient are meters squared per second, and the units of spacing are meters. So if you divide meters squared per second by meters, you get a velocity or a speed, which is meters per second. So if the interface velocity exceeds the ability of atoms to jump away from the interface, then you get diffusion-less growth. So this is a very basic and very simple equation, which tells you that if your interface velocity exceeds this number, the diffusion coefficient divided by the interatomic spacing, then there is no time for atoms to move out of the way, even though they may not prefer to be inside the martensite. So I'll come back to how to calculate this velocity later. But the interesting thing here is that what is this diffusion coefficient? Well, if we are just looking at an iron-carbon system, then this is the diffusion coefficient of carbon in austenite, and this is the diffusion coefficient of iron in austenite. And obviously, this is many orders of magnitude smaller than that of carbon, because carbon sits in interstitial sites and can diffuse much more easily than the iron atoms. So in this equation, we have to use the diffusion coefficient of iron, because that is the rate limiting factor. Okay, so this is the fundamental condition for diffusion-less growth, that the velocity of the interface must exceed the rate at which atoms can move out of its path, and that this interfacial velocity actually depends on the undercooling, the driving force that's available. So if you take austenite and you suddenly quench it to 700 degrees centigrade, there will be a certain delta G, a change in free energy. And if I cool it to a much lower temperature, then that delta G will be much larger in magnitude. So you expect the velocity of the interface also to be greater. So the relationship between the velocity of the interface and the driving force comes later in the lecture. So there are two reasons for diffusion-less transformation. One is that you need a small diffusion coefficient, and you'll find this in all books, etc. That obviously if the atomic mobility is limited, then the only way to change the crystal structure is by a displacement mechanism. But people often forget that if you have a large driving force, then the interface can move much more rapidly than atoms can diffuse. So we expect, martensitic transformation in pure iron to happen at a higher temperature than martensitic transformation in an iron-manganese alloy, because the driving force for transformation in pure iron is much greater than in an iron-manganese alloy. Now, what is the consequence of what we have discussed so far? Well, in the second slide, I showed you how the lattice is deformed into a different shape. And imagine that that crystal is surrounded by many other crystals. Then it's pushing against its surroundings. And that will cause a lot of strain energy. Okay, that strain energy is enormous. And at the same time, atoms which don't really want to be inside the martensite will be forced to be in there because the velocity of the interface is very high. And we call that solute trapping. So martensitic transformations are going to be far from equilibrium because there's a huge strain energy associated with the deformation. And we will also store energy because some atoms, for example, carbon, really don't want to be inside the martensite, but are forced to be inside the martensite. And that is called solute trapping. It's the free energy of a carbon atom actually increases in going from austenite to martensite. Okay, so that means that it is forced to be in the martensite, even though it does not want to be there. So I did some calculations on these quantities for a typical steel, iron 0.2 carbon, 1.5 manganese, and transformed at 300 Kelvin, which is quite a low temperature. And my reference state is that we have a mixture of cementite, graphite, and ferrite here. And I assign a stored energy because of the deviation from equilibrium to be 0. So this is an equilibrium mixture of the three phases. So people often say that graphite is more stable than cementite, but really you have to think about what the phases are in equilibrium with to make that statement. And in this case, at 300 Kelvin, all three phases are stable. There's a 0 stored energy. So this is our reference state. Now, if I force the calculation to abandon graphite, okay, then immediately the deviation from equilibrium becomes larger. We have 70 joules per mole of stored energy. And in this case, the manganese is partitioning between the ferrite and the cementite. But if we force the manganese not to partition, only the carbon is partitioned between the phases, then you get a dramatic increase in the stored energy. So this is what we call para-equilibrium, where the large atoms are not diffusing at all, but interstitial species like carbon partition, and that's why you get cementite. Then if you have bainite and cementite in a para-equilibrium state, then once again you have a large increase in stored energy, because this, you will see later, also has a strain energy term. And martensite has the greatest stored energy, 1,200 joules per mole, which is really quite large. And that means you have to undercool the austenite quite a lot while avoiding any other transformation in order to obtain martensite, because it's so far from equilibrium. And just to give you an idea of nanostructured iron, in which the grains are really, really small, Okay, and you might have produced this by mechanical alloying, or you might have produced it by very severe plastic deformation, in torsion, etc. But grain boundaries themselves don't have that much of stored energy. And that's why this term is actually quite small, only 55 joules per mole. Okay, so it's easy to get transformation at low temperatures by a displacive mechanism, but there are consequences that a lot of the energy is stored inside your material and it is far from equilibrium. So if you give it a chance, for example, by tempering, then the situation will change. Whereas a structure like this, it doesn't matter how long you hold it, it will not change from the equilibrium mixture of graphite, ferrite, and cementite. All of these will change if you anneal the material. Now let's contrast displacive transformation with a transformation which must have a diffusion flux. So this is a schematic illustration. Here we start off with the same austenite with this unit cell, and we break all these bonds, and we simply rearrange the atoms into a different pattern without changing the external shape of this object. Okay, and that means that you must have had diffusion in order to eliminate that shear deformation that we had in the previous slide. You must have had diffusion in order to avoid that strain energy associated with the shape change. Now, if you are getting diffusion, then you will also get partitioning. So for example, in this case, all the red atoms have moved into the product phase, the ferrite. Okay, so people often talk about diffusion happening on the length scale of an interface, but actually you require it to happen over a larger length scale in order to achieve reconstructive transformation, where you break all the bonds, you have diffusion fluxes, and that changes the crystal structure. And typically the diffusion should occur over the length scale of the transformation product. So you could take the length scale as that, or if it is like a plate, then over the length scale of the plate, and so on. And here I'm talking about transformations which leave only a small amount of stored energy in the system, because we may not precipitate graphite in a typical steel. Okay, let's go and address this problem about diffusion over the length scale of the product, because that can help us to define the domain in which we will get reconstructive transformations and displacive transformations. You know, if you cannot get diffusion over the length scale of the product, then you will get a displacive transformation. So I did some calculations using an equation for interfacial velocity, where the velocity varies with the magnitude of the driving force here. Okay, and this is the largest interfacial mobility that I could find for an incoherent interface in the literature. These numbers here are very uncertain, so I should warn you that they can vary by orders of magnitude. But I've chosen the largest one to give you the greatest mobility, as an approximation. And I did this calculation of the distance moved by an interface in 1 hour. So this is 3,600 seconds. This is the distance moved by the interface, and this you can calculate using, all the CalFED methods. I did the calculation for pure iron, for iron 1.5 manganese, and iron 0.2 carbon 1.5 manganese. And you can see that the velocity or the distance moved in a given time actually goes through a peak. And the peak is because here the driving force is small. Whereas here the diffusion, effective diffusion coefficient, it's not a diffusion coefficient, it's an interface mobility, becomes small. Okay, so this term decreases exponentially with decreasing temperature, and this term decreases as you go towards the equilibrium temperature. So in pure iron, you will get very rapid movement of the interface. If you add 1.5 manganese, then basically this term is decreasing, okay, in magnitude. You're reducing the driving force for transformation from austenite to ferrite, and therefore you end up with a lower interfacial velocity, and carbon has a similar effect. Now, what I want you to notice is that suppose I choose that my transformation product is 5 micrometers in size. Okay, so this dashed line represents 5 micrometers. Then below this temperature range here, which is approximately 530 to 515, displacive transformations will happen because you cannot get diffusion over the length scale of the transformation product. Whereas here, the austenite is quite happy to transform by a reconstructive mechanism. So this gives you a clear way of saying that, look, below this temperature, I should obtain displacive transformation products, and above it, I should be able to obtain things like ferrite, pearlite, etc. And the interesting thing is that if I now show you time temperature transformation curves here, so these are for a variety of steels, and this upper C curve represents reconstructive transformations, and the lower C curve represents displacive transformations, then actually, the point where displacive transformations are kinetically favored. So here, for example, displacive transformation is faster than anything you could produce by reconstructive transformation. This regime is approximately the same as what I showed you in the previous slide, the temperature range over which you give way from things like ferrite and pearlite to bainite and martensite. Okay, so this should give you a clear picture of the domains in which you can get either reconstructive or displacive transformation as a function of the slowest diffusion coefficient and of the magnitude of the chemical free energy change when austenite changes into your product. Now, steels are absolutely wonderful materials. They are so incredibly successful that we have to bring their use under control. So we are using something like 1.6 billion tons of the material every year, and that is far too much. Now, one of the reasons why they are so successful is that there are literally thousands of phase transformations that you can get in steels. And therefore, you can control its properties over a very, very large scale. Whatever property it is, you can control it by manipulating the phase transformations. I'm only going to show you some of the phase transformations. So this is a chart showing you the displacive transformations and the reconstructive transformations. I'm not going to talk about carbides and other kinds of precipitates that can also change this scenario, but these are the major transformations. So here we have, people call it grain boundary ferrite, but it's more accurately called allotriomorphic ferrite because its shape does not reflect the crystalline symmetry. It's simply that it's growing rapidly along the boundaries. Idiomorphic ferrite means we have intragranularly nucleated ferrite. Massive ferrite, I'll come back to in another lecture. And pearlite, everybody knows what pearlite is. This is one of the original pictures from Bain's, Davenport and Bain's laboratory at US Steel. This is Wiedmannsstatten ferrite, which I obtained from the Catholic University in Peru. Wiedmannsstatten ferrite plates, bainite, and martensite. Okay, so even within the displacive transformations, there are different characteristics you have, and we will learn about all those characteristics later so that you can accurately calculate when Wiedmannsstatten ferrite is going to happen, when bainite will happen, and when martensite will happen, and so on. Okay, so let us now return to martensitic transformation because it is very simple. Everything is diffusion-less, both nucleation and growth. So at this point, I normally start off by reviewing what people know about martensitic transformation. So what do you understand by martensitic transformation? And what are the characteristics of martensite? Well, if you ask this to second-year undergraduate students, they will come up and say, yes, martensite is hard. Okay. Someone else might say that you need to quench the austenite rapidly in order to obtain martensite. Someone else will say, you know, the shape is like plates or laths. And unfortunately, the term needle is also often used. That it's displacive. Many people know that it involves a large shear deformation. They will say there's a volume change because the density of austenite is different from that of martensite. And that is brittle. Martensite is brittle. That is a common thing that second-year undergraduates might perceive. It has a crystal structure which is body-centered tetragonal in steels. It is metastable. We've already described that, you know, because it deviates so far from equilibrium, if you heat it up, it will tend to change because you allow atoms to go towards equilibrium. And it's diffusion-less. Okay, let's challenge each one of those aspects first. And you know, you have to realize that although martensitic transformations are the most important in steels, there are many, many materials in which you get martensitic transformation. So for example, here is an image of titanium carbide in which we have martensite plates. Okay, imagine titanium carbide is so hard, but you can induce a martensitic transformation inside that carbide. And you know, it doesn't actually have to form at a low temperature. It just has to happen at a temperature where atoms are not mobile. And in ceramics, that can be quite a high temperature. So zirconia, for example, undergoes a martensitic transformation. I think it's between cubic and monoclinic. And of course, because it's a ceramic, you know, the bonds are very strong, and therefore you have a hardness of something like 1,000 Vickers. Here are two alloys of nickel and carbon, and look, here the martensite-start temperature is less than 4 Kelvin. So this tells you that the transformation can happen at a very low temperature, okay? And it can happen at a very high temperature. So temperature is not a good parameter to say whether or not martensite should form. It's basically that atomic mobility is limited and the driving force is small. Those two terms must go together. So here, for example, because we have a lot of nickel and carbon, the driving force for transformation is very, very small. Okay, and therefore you have to cool to a really low temperature before there is sufficient driving force for displacive transformation. Okay, this is a typical steel which will have a high transformation temperature. And you know, sometimes when you have a high transformation temperature in steels, it may be the case that the martensite tempers at the same time as it forms. So you end up with a microstructure in which you will have some evidence of tempering, for example, the precipitation of transition carbides. Now, martensite does not have to be hard, even in iron. So Malaysian steels, for Malaysian iron alloys, which have almost zero carbon, have a hardness of just 350, you know, more or less like that of pearlite. So that gives us a clue that it is really this element which is causing much of the hardening of martensite. And we can get it in copper aluminium alloys, in argon nitrogen solid solutions, and in many other metallic alloys. So in plutonium, for example, there is a whole series of martensitic transformation as it cools from the solid state. So when it forms solid plutonium from liquid plutonium, it's actually less dense than the liquid. Okay, it's a bit like ice and water. Ice floats on water, even though it's a solid. So plutonium, when it solidifies, is much less dense than liquid plutonium. So during cooling from about 500 degrees centigrade, it has a low melting temperature. It will undergo a series of martensitic transformations, 3 or 4 martensitic transformations, which cause it to densify at the same time. So there are many materials in which we get martensite, but undoubtedly the biggest, by far the biggest, by many orders of magnitude, the biggest applications come in iron alloys and steels. Now, we noticed from this that, you know, if you don't have carbon, then the hardness of martensite need not be very high. Okay, and that is reflected in many empirical equations that have been developed. And one of the best equations comes from this work by Blondeau et al. In France, where we have the hardness of martensite. This you could imagine is the strength of the iron and includes some dislocation density terms. So sometimes people say martensite contains a high dislocation density, but that is not true. Otherwise, you would never get shape memory alloys. You only get a high dislocation density if there is some sort of plasticity caused by the high temperature at which martensite forms. Okay, so this is quite a small term. Look at this term. Okay, this is the weight percent of carbon, really huge hardening effect. Whereas the substitutional solutes have really quite small effects, and this is a cooling rate in degrees C per hour. Now, I said to you that if martensite forms at a high temperature, then even though it forms in a completely diffusion-less transformation, it can temper because you are at a high temperature. So you might get the precipitation of transition carbides and so forth. So this is a really nice equation because it takes account of cooling rate on hardness. Okay, and the cooling rate is reflected in the time available for the martensite to temper before you get down to room temperature. Now, the interesting thing is that carbon doesn't harden austenite very much at all. Carbon in austenite behaves like a substitutional solute, very little hardening. So here is a graph showing you the hardness of martensite as a function of carbon, and you can see it increases. This is an artifact because we start to get retained austenite. So this is hardness is lowered because you're no longer measuring the hardness of pure martensite. But if you just measure the hardness of martensite, it increases monotonically with carbon concentration. Look what happens with austenite. Hardly any change in hardness. Why is that? Why does carbon greatly influence martensite but not austenite? The reason is very simple. This is austenite, and this is the position of the carbon atom. And of course, it doesn't fit inside that position. But the strain that you get because of that misfit is isotropic. This length here is the same as this length and this length. So it's just a volume change, right? And the volume change is a hydrostatic strain. It doesn't interact very much at all with shear, which is the strain field of a dislocation. And therefore, it behaves like a substitutional solute. It only interacts mildly with dislocations. Dislocations are about shear, and the volume change doesn't affect that very much at all. Doesn't affect the mobility of the dislocation at all. On the other hand, in ferrite, okay, this similar octahedron is actually squashed along this direction. So this length here is the same as the edge length of the unit cell, but this and this are √2 times the edge length. Okay, so there's much more space in these two directions than in this direction. So you cause a tetragonal distortion, and a tetragonal distortion can interact strongly with dislocations because dislocations are about shear, and an anisotropic strain interacts very strongly with dislocations. And it is purely, the symmetry of these two lattices, ferrite and austenite, that causes this intense hardening in martensite, but hardly anything in austenite. Very interesting. Okay. Right. People sometimes say that twinned martensite, the twins are what are causing strengthening, but that idea was, dismissed many years ago by comparing the strength of lath martensite and twin martensite, and they're not particularly different. Okay, so you've seen, how the crystal structure itself has a dramatic effect on mechanical properties. I'm going to return now to the strains caused by martensite when it forms, because that forms a very large deviation from equilibrium. So martensite is to be regarded as a physical deformation. Okay, which at the same time changes the crystal structure. And it's illustrated beautifully in this movie, which is a shape memory alloy which has been cooled, right? And now it's going to be put onto a hot plate. And you get a reversal of the martensitic transformation, and therefore it changes its shape. And if you put it back into the cold liquid, which is probably liquid nitrogen, then it will go flat again. Okay, and that sample is actually polycrystalline. Nevertheless, the shape deformation of the martensite is causing that macroscopic shape change. And these, of course, are the shape memory alloys. And shape memory effect would not work at all if you created a lot of dislocations during the forward and backward transformations. So the dislocation density is not an intrinsic feature of martensitic transformation. It's caused when there is some plastic relaxation because you're forming martensite at a high temperature where the austenite is quite weak. And of course, this is a single crystal here, okay? But in this shape memory material, you have a polycrystalline array of martensite plates, which when you reverse and allow the transformation to go in the forward direction, also causes a macroscopic shape change. And you can get shape memory alloys in the iron system. They're not so reversible as in the nickel titanium system, but they are useful in applications where you have just one reversal necessary. For example, when you're trying to join two tubes together, you don't need to go forward, reverse, you just need the tube to contract and clamp the tubes together. Now, I've emphasized that martensitic transformation is diffusion-less. Okay, how do we know that? How do we know that martensitic transformation is diffusion-less? Well, we've already proven that it can form at incredibly low temperatures, 4 Kelvin, for example, where it is inconceivable that there is any diffusion. We have, of course, we can form at high temperatures in materials where the bonding between atoms is not metallic, it's very strong, such as zirconia. It can form so rapidly that you can hear the transformation. Okay, you get acoustic emissions from the material, and you only get acoustic emissions if the transformation is sufficiently rapid. So it approaches something like 1,000 meters per second in some systems. Now, that doesn't mean that martensite cannot grow slowly. You've just seen a movie of the shape memory effect where it's not happening rapidly. It's happening at an observable rate. If you put a microscope there, you can see the interfaces moving, okay? So not all martensitic transformations are rapid, just as not all martensitic transformations happen at low temperatures. There is no composition change. Well, there are many, many modern techniques with which we can prove that, for example, the atom probe and so forth. So that is the evidence that the transformation is diffusion-less. What about the shape? Well, in books and other places, people call these needles, but that is completely wrong, okay? Because we are looking at a two-dimensional section. These are not needles, they are plates in 3 dimensions. If they were needles, then we would be able to see some cross-sections which are round, and we do not see any round cross-sections in this image. But you know, when I say that it's a plate, as soon as you get many plates forming, right? If you had a single isolated plate, it would be a nice, beautiful plate, rather like this, with a smooth interface, okay? But when you have many plates forming together, there is real complexity, okay? So I'm just going to blow up 2 regions of this micrograph, here and here, to show you how the strain interactions between the different plates mess up the microstructure while still remaining a plate shape. Okay, so you can see here the plate has broken up into tiny, tiny plates because the strain energy accumulation is too much to tolerate for a thick plate. The thickness of the plate and its relationship to the strain energy will come later. Now, there's another thing that I want you to notice. So, a blown up region of this area here. You can see these plates here. What's happening is that the strain field of a martensite plate that forms first is stimulating other plates to form, because martensite is a physical deformation. So it will react to any strain fields or an applied stress. So these plates are what we call autocatalytically generated plates. So supposing you have a nucleation rate of martensite, that rate increases dramatically after the first few plates form because of the strain interactions and possibly also some defects produced. Now, I said to you that if these were needles, we should be able to see some round sections, and I'm going to show you another micrograph of a product which truly is in the form of needles which form along the 100 direction of ferrite. So these are molybdenum carbide needles, and the way that I know they are needles is, look, can you see these round cross sections which are poking out of the plane of the diagram? We don't see any sections like this in the previous optical micrographs that I showed you. Okay, so the transformation product is in the form of thin plates. Now, supposing you had a single crystal of austenite and you transformed it partly to martensite, it's just pushing against air, okay? So there is no strain energy, but there is a change in shape. However, if this is surrounded by many other crystals, as it would be in a polycrystalline material, so that we call constrained austenite, then it will tend to form as a thin plate. And the reason for this is that a thin plate is the best shape to minimize the elastic strain energy around the martensite plate. And you will notice from these micrographs that the tips of these plates are very, very thin. And I'll be able to explain that later when we look at the quantitative strain energy due to the formation of a martensite plate. Okay, so this is unconstrained transformation and constrained transformation. Now, this interface here between the parent and product is called the habit plane. And even in constrained transformation, this average plane is the same as this in crystallographic terms. However, this plane is complicated. It is not rational. That means it's not a closed back plane. It's got very strange indices, and even these indices are approximate. So it isn't exactly 31510 austenite, but a deviation from that, which makes it impossible to express the indices as integers. So whatever theory we have, it has to explain why we have these very peculiar indices, approximate indices for habit planes, whereas when we get slip, it happens on closed back planes and closed back directions and so forth. But martensitic transformation, with some exceptions, okay, happens on irrational habit plane indices. The exception we'll deal with in the second lecture. So I'm just posing questions at the moment. We will solve them later. Now, returning to the shape of the martensite, this obviously would be the habit plane here, the average habit plane. And if it was unconstrained, then this would be a very accurately defined habit plane. We need to be able to explain this shape in more detail. Another question mark, okay? Now, the third question mark will come when we talk about orientation relationships. So obviously, if you are generating the product from the parent by a deformation, then they will be systematically related in space. So this is the classic Nishiyama-Wasserman orientation around 1945, independent measurements, where we have the most closely packed plane of the martensite and the close back plane of the austenite exactly parallel. And there is an angle of 5.26 degrees between the close back directions within these planes. There is a clear relationship between the Nishiyama-Wasserman and the Kurdjumov-Sachs orientation, just a rotation of 5.26 degrees, about the central pole. Okay, so they're not very different. If you look at those orientation relationships, the martensite cell is inclined to the austenite cell. But actually, those orientation relationships are approximate. They are not exact. The real orientation relationships are irrational. That means that we don't have exactly parallel close-back planes from the two lattices. There is a small angle between them, and similarly for the directions. So you should regard the Nishiyama-Wasserman and Kurdjumov-Sachs orientations as approximate, and this matrix actually defines approximately the irrational orientation. So if you multiply this by any column vector, you will change the indices from ferrite to austenite. Okay, so we need to explain why the actual orientation is irrational. Okay, just like the habit plane. Okay, now almost all the time temperature transformation diagrams will indicate that if I cool the austenite to this temperature, I will get a certain amount of martensite. But to get more martensite, I need to cool further. Holding at this temperature will not change the amount of martensite. Okay, so if I cool to this temperature, I get 50% martensite, 95% martensite lower temperature. But isothermal holding makes no difference. Okay, now that is known as an athermal transformation. That's unlike, for example, pearlite. If I hold at this temperature, I will get more and more pearlite until the austenite is consumed. And that athermal temperature, athermal behavior, can be explained by Koistinen and Marburgen's famous equation, where this is the volume fraction of martensite. This is a constant, which is minus 0.011. This is the martensite-start temperature, and this is the temperature below MS. Now, notice that there is no time in this equation. In order to get more martensite, you have to cool further. Okay, so this is called athermal transformation. Now, the reason for this behavior is that our experimental measurements are approximate when the transformation happens extremely rapidly. So let's imagine this 1% here. If you had enough resolution, you would see individual martensite plates growing, and they take a certain time to lengthen. But if that is very rapid, then your time resolution is not enough to see the progress of the transformation. So you get 1% transformation happening actually isothermally as a function of time. And once the nuclei are exhausted, you won't get more than 1%. All right? And therefore, you have to cool further to activate more difficult nuclei and so on. And there was a very famous experiment done in Russia by Kurdjumov and Maximova, which is illustrated here. So if you form martensite at an incredibly low temperature, then you can actually pick up a time temperature transformation diagram like pearlite, where this is a C-curve indicating the amount of martensite that forms as a function of time. So you quench your austenite to this temperature and you hold it. It will take longer because this temperature is smaller. And if you quench it to this temperature, it will take longer than an optimum temperature, just like the C-curves that you see for pearlite. So it isn't truly an athermal transformation, but in order to pick up the time dependence, you have to form it at a sufficiently low temperature that it slows down. Okay? And this experiment was in 1948, and many people in the West did not believe it. But I think Maurice Cohen and his colleagues at MIT, who were also working on martensite, immediately caught on to this. Okay, so truly speaking, martensite is isothermal. You can get more martensite as a function of time, but if that happens so rapidly and you exhaust all the nuclei, then it's not possible to form further. And if our time resolution is not good, then you will not pick up the time dependence, given that plates can form at 1,000 meters per second. Okay, let's look at the structure of the interface. And I need to introduce to you the definition of an interface, okay? So supposing we start off with a single crystal here, and then I slice it into half, and then I tilt the two halves of the crystals relative to each other. Then I should have a boundary here, but in fact I have a space left, okay? What can I fill that space with? Well, notice that this tilt here by this angle theta, okay, looks exactly like this tilt here, which we have when we have an edge dislocation, right? So this is an extra half plane, and we've got this tilted lattice on each side. So if you fill that space in the previous diagram with a set of dislocations, then we have a true interface and no holes left, okay? So here we are. We have now filled it with a number of dislocations, and the number and spacing of dislocations and the magnitude of the dislocation, the Burgers vector, will determine the nature of the boundary between these two sides. But there are only very special interfaces that can achieve martensitic transformation. Okay. This is just a geometrical relationship between the magnitude of the Burgers vector of the dislocation, the spacing in the interface, and the misorientation between these two sides. So if I have an array of dislocations like this, where the Burgers vector is pointing out of the plane of the interface, then of course this array of dislocations can glide, just like a dislocation gliding to achieve deformation. There's no diffusion necessary for a glissile interface to move. But if the dislocations have their Burgers vectors in the interface, then they have to climb in order to move the interface to a different position. And that is impossible for a martensitic transformation. So the structure of a martensite interface must be such that the dislocations can glide and achieve the change in crystal structure and the physical deformation without diffusion. Okay, so that's illustrated over here. This is a glissile interface, and when it moves, you will see that it changes the shape of the parent product. Okay. This is now moved to a different position, and you can see that the overall shape of the bicrystal has changed as a consequence of the deformation. Okay, so that's a glissile interface. There's a further condition that we cannot have more than one array of dislocations in the interface. Okay, you must have only one set of parallel dislocation lines. You cannot have two sets of dislocations, because if you do, for example, here and here, then when they move, they will cut each other, okay? And they will introduce what's known as a jog, okay? This is a jog, a step in the original dislocation line. So this is a screw dislocation, but now it has an edge component, so it cannot glide, right? Because the line vector here is not the same as here. And similarly, we've created a jog here. The Burgers vector is the same along this, but the line vector is not. So what happens is that these dislocations interfere with each other and create steps which become sessile. That means they cannot move without diffusion. And that's a problem for martensite, okay? So if you look at a very high resolution at a martensite-austenite interface, then you will only see one set of parallel lines, because having more than one set means that you would get interference and the structure of the interface would become sessile. It cannot move without diffusion. Now, how can we have an interface with just one set of lines? Well, you must have perfect coherency along the line of the dislocation, so there's no need to accommodate misfit normal to that line. And this brings us to a very fundamental principle, okay? Very fundamental principle, that a glissile interface cannot contain more than one set of dislocations. And martensitic transformation is only possible if the gamma to alpha prime deformation leaves one line undistorted and unrotated. In other words, fully coherent, right? It's neither change in length nor is it rotated. And we call that an invariant line. It is not changed in length or orientation by this deformation. So the deformation is an invariant line strain. The deformation which carries gamma into alpha prime must leave a single line unchanged. Now, supposing that you wanted to find out whether, magnesium can undergo martensitic transformation from its hexagonal structure to something, let's say, cubic structure. If you cannot find a deformation which will change the hexagonal to cubic and leave a single line undistorted and unrotated, then it's impossible to get martensitic transformation. Okay, so if you have two hypothetical crystal structures and you want to see whether you can transform from one to the other by martensite, if you cannot find a deformation which leaves a single line undistorted and unrotated, then it's impossible. Okay, so your interface will look like this if you look at it in plan view. Only one set of dislocations, and the invariant line between the two lattices lies along these dislocations. And this is why the interfacial energy of martensite-austenite interfaces is so low. So just to give you a comparison, this is a table of typical interfacial energies. So between martensite and austenite, it's about 0.2 joules per meter squared. A coherent twin boundary is about the same. Okay, so there's a high degree of coherency between the gamma and alpha prime interface. An incoherent boundary, a typical grain boundary, would be 4 times higher energy. And the surface energy of window glass is about 1. It's basically an amorphous material. So you have to have this high level of coherency in the interface, only one set of dislocations, and the dislocation lines lying along an invariant line. Okay, let's see if we can transform austenite to martensite. These are the two crystal structures by a deformation which is an invariant line strain. Well, first of all, I've already demonstrated to you that we can change lattices. Here we have a square pattern, and we can, without breaking any bonds, we are going to change the arrangement of atoms. Okay, but as a consequence, we will see a shape deformation. Right, the macroscopic shape of the crystal has changed, although the lattice type has changed at the same time. So martensitic transformation, I emphasize again, is a combination of a phase transformation and a physical deformation. So the next movie is one of the beautiful movies made in Germany, showing you an actual shape deformation happening on austenite, which has been polished organically flat and then is cooled. So this is in German, but this is a hot stage optical microscope.
Unter einem Mikroskop mit einer Heiz- und Kühlvorrichtung kann die Schliffoberfläche während der Abkühlung beobachtet werden. Die Martensitbildung wird in der polierten Oberfläche durch eine nadelförmige Deformation sichtbar. Bei 830 Grad Celsius sind von Austenit lediglich die Korngrenzen zu sehen.
So
Dieses Bild ändert sich mit der jetzt einsetzenden Abkühlung so lange nicht, bis die Temperatur des Beginns der Martensitbildung bei 360 Grad Celsius unterschritten wird. Man erkennt kein Wachsen der Nadeln. Hier eine Übersichtsaufnahme. Die einzelnen Platten entstehen etwa mit Schallgeschwindigkeit. Die Martensitmenge nimmt nur mit sinkender Temperatur zu.
Amazingly beautiful movie, okay? Done a long time ago using a hot stage optical microscope. Okay, this is another movie showing the shape deformation, but this time in a shape memory alloy. So in steels containing carbon, the transformation is not very reversible by changing temperature, because if you go to a higher temperature, then the martensite will temper, and therefore, you've changed the configuration of the martensite. But in other alloys, and this is a non-ferrous alloy, you can get reversal of the transformation, which you'll see shortly. This is made in a university in Hungary. So we are now reversing the transformation, okay, by heating up the material. So you see, by reversing the transformation, the austenite once again becomes completely flat. So you've completely reversed the deformation that's caused by the formation of martensite. It really is amazingly beautiful to look at. Okay. Right. So what we see in those movies is a shape deformation. So if I take a crystal and I pass a dislocation through it, then I will get a step. And if I move an array of dislocations, I will get a series of steps like this, which with the resolution that we were looking at looks like a homogeneous shear, but actually it's being accomplished by an array of dislocations. And here, if you had sufficient resolution, for example, in a transmission electron microscope, you would see the steps. These are not slip dislocations, they achieve transformation, so they are partial dislocations. And the nature of the shape change is not actually shear. So a shear would not accomplish a volume change. We need to combine the shear with a uniaxial dilatation like this, and that would give us what we call an invariant plane strain, which leaves this plane completely undistorted and unrotated, a coherent plane. And typically in steels, the shear strain is 0.26. Now that is huge, okay? So if I take a steel and I apply a stress of 200 megapascals, then given that its modulus is about 200 gigapascals, the strain would be 0.001, okay? This shear strain is massive, it's 0.26. And this is the volume change, which is about 3% and normal to the habit plane. It's not an isotropic volume change, okay? Very important to note that. Now, the consequence of this is that we get a lot of strain energy if it's happening in a polycrystalline material. And Czech Christian, back in 1958, used Aschelbe Theory for the first time to give us an equation, which I'm expressing approximately here, of the strain energy per unit volume. C and R are the thickness to the length ratio of the plate. Mu is the shear modulus of the austenite, and this is the shear strain squared and the volume change squared, right? As I showed you in the previous slide. Now, Aschelbe theory is really quite complicated, so I'm going to explain this in a simple way. Now, supposing I take a piece of metal and I, apply a stress torr, and that gives me a strain gamma. So this is a shear strain and this is a shear stress. And Hooke's law tells us that this is a linear function and that the area under the curve, which is half tau times gamma, the shear strain, stress times strain. And if I replace the stress by the modulus times the strain, then this would give me the strain energy per unit volume, the area under this curve, okay? Now notice the similarities here. We have the strain squared and we have the shear modulus here. Now this half is missing because this is a plastic deformation. It's a permanent deformation. This is an elastic deformation, right? The only thing that cannot be explained by this, by what I've just said, is this term, which requires Aschelbe theory, that the thinner the plate is compared with its length, the smaller is the strain energy per unit volume. But of course, you are transforming less material. Therefore, plates will be thicker if you have a large driving force to sustain the strain energy of a fat plate, right? Plates will be thinner if the driving force is small and therefore you can't account for the strain energy, all right? When we come to discuss nanostructured material, this will become important. Now, this gives you a method of calculating the thickness of a martensite plate. Now, supposing you have an austenite grain here, martensite cannot grow across austenite grain boundaries. It's impossible because you can't get a coordinated movement of atoms when the orientation changes. So if you assume that the length of the plate is given by the mean linear intercept of your austenite grain size, and you know the chemical free energy change, you set it equal to this, then you can calculate the thickness, set this as the austenite grain size, and use 0.26 and 0.03, and you'll be able to work out the thickness of the martensite plate, as long as you can work out the driving force for transformation using one of the Calfred methods, which are so popular in the University of Udine. Now, I'm going to stop here, but I'm going to summarize the difficulties that I have not solved as yet for the next lecture. So we have strange habit planes, like 3, 10, 15, and furthermore, it's not exactly 3, 10, 15, all right? Whereas plastic deformation happens on very reasonable planes, like 1 on 1. We have a strange orientation in which the closed back planes are not exactly parallel. You can measure a small angle between them, and similarly for the closed back directions. And we have to demonstrate that this shape deformation, which is an invariant plane strain, is consistent with the crystal structures and also leaves one line completely coherent between the martensite and the austenite. Okay, so I will continue with this in the next lecture where we will solve these problems, and I'm very happy to answer any questions that you may have.